with almost minimal time and space overhead. And it's by Justin Ongren and Ron Rothblum. And Justin will give the talk.
Thank you. Okay, so I guess the first question is, what is delegating computation? So delegation is about a protocol between two parties, a computationally weak client, which here is depicted by an Apple Watch, and a powerful server, which here is depicted by a cloud. So the client is trying to evaluate some expensive function f, and it's enlisting the help of a cloud. So there are several very important properties that we would like any delegation protocol to satisfy. So first of all, when everybody is following the protocol and there are no errors, then the client should output the correct value, y equals f of x. But what about when the cloud is misbehaving or is untrusted? Well, one thing a malicious cloud could always do is just refuse to participate in the protocol entirely. And there's really nothing that you can do to defend against this. But this is not so bad, because in this case, the client can just output error or bot or whatever you want, and then you can handle it however you'd like. So we'll require that for a malicious cloud, this is all that the cloud can accomplish. In particular, it cannot cause the client to output some incorrect y. So far, this is all trivial to accomplish. The client can just compute f of x on its own and ignore the cloud. So to rule that out, we'll just require that, that the client runs in nearly linear time, and we'll imagine some functions f that are much more expensive than that. And in general, we'll call the cloud the prover, and we'll call the client the verifier, because that's what they're doing. They're proving and verifying. So delegation is a very important problem in practice. Lots of people have designed protocols. There have been a lot of implementation projects. But it's actually very far away from being practical. And the main reason for that is the overhead that's incurred by the prover. So first of all, in running time, in a lot of the existing protocols, the overheads that we talk about are on the order of like trillions of times faster or slower than the basic computation. But moreover, the space usage is a real problem. In a lot of these protocols, the prover has to write down an entire transcript for the computation. And this can quickly become a hard limit if once the computation becomes long. Okay. So what about in theory? Which is, we're at a theory conference. So here we'll try to look at the asymptotics of the prover overhead, as well as the hardness assumptions that we need to make in order to ensure that the protocol actually is sound. So the most relevant to us is a line of work initiated by Kalairaz and Rothblum, since been a few follow-ups. And this line of work achieves delegation protocols that have a polynomial overhead for the prover under the assumption that there exists some private information retrieval protocol, a single server private information retrieval protocol. But this polynomial overhead that they achieve is actually very bad. They didn't actually try to explicitly optimize the exponent, but it's at the very least 3. And moreover, this is with respect to the Turing machine running time to evaluate this function. Obviously, a slightly more realistic model would be a RAM model of computation. So in this work, we improve the prover overhead quite significantly. We use a slightly stronger assumption, assuming that somewhat homomorphic encryption exists. So we basically essentially match the RAM running time of computation. And in the case of Turing machines, we can also do slightly better, getting a polylog additive overhead in space instead of just sublinear. I also want to mention that there have been a couple of other works that achieve similar efficiency for the prover, and as well as several other desirable properties of a delegation scheme from more exotic and more difficult to understand computational assumptions. Okay, so the main tool in our construction is probabilistically checkable proofs. Many of you are probably familiar with these, but let me just remind you what they are. So probabilistically checkable proofs, or PCPs for short, are a way to write down a proof that can be verified by looking at just a small number of random locations in the proof. So they're checkable very, very efficiently. And PCPs have analogous completeness and soundness requirements. If they're in reference to a true statement, that f of x equals y, then there should be a convincing proof, and if not, then every proof should be rejected with high probability. But yeah, so far this sounds like a delegation scheme, but it's really not, because the proof string is very long. The verifier doesn't even have time to receive this entire proof string. However, you can use a probabilistically checkable proof to construct a delegation scheme, at least heuristically. And the basic idea is that instead of just having access to a string, the verifier will ask the prover to provide whatever symbols the verifier is interested in. This would be completely unsound, but the heuristic is to hide which symbols the verifier is actually interested in using a private information retrieval protocol. So this heuristic is, in general, not going to be sound, but it actually turns out to be sound if the PCP satisfies a stronger notion of soundness called no signaling soundness. And in the context of caring about the prover efficiency, what matters here is how long it takes to generate the entire PCP proof string. But yeah, so a very basic observation that you can start with is if instead of using just a generic PIR, if you use a fully homomorphic encryption scheme, then it's not any more necessary for the prover to construct this entire string. Instead, you sort of just need random access to the PCP. You need to be able to efficiently compute, given j, the jth symbol of the PCP. Okay, so how can we start to go about doing this? Well, I'll give you like a super high-level outline first. Maybe it'll sound like stupid because it's so high level, but we'll see. So the first step is to prove that a very simple PCP, so namely the classical construction of Labai, Fortnow, Lund, and Szegedy, actually satisfies no signaling soundness. So simplicity is always good. Our analysis remains complicated, but the simple construction allows us to identify lots of sort of repeated subcomputations in the naive algorithm for computing this PCP. And as you all know, if you've ever taken an algorithms class, repeated subcomputations let you do these sort of time-space trade-offs where you don't recompute things, you just store the result. But the time-space trade-off that we end up getting is not actually great, but we show that you can kind of avoid any real time-space trade-off by doing appropriate caching. You don't actually need to remember all the subcomputations, you can just remember a few at a time. Okay, so that's the high-level outline. I'm going to spend basically no time talking about the no signaling soundness analysis. I'm going to give you a sort of brief view of what the BFLS construction looks like, and then I'll talk about some of the sort of efficiency improvements that we do in the computation of that proof string. Okay, so first of all, the most basic ingredient in any PCP is the idea of looking at a computation transcript. Suppose you have your function f and it's computable by a Turing machine. We'll just stick with Turing machines for pretty much the remainder of the talk. So f of x is going to be equal to y if and only if there is a computation transcript that supports this fact. So a computation transcript is you sort of write down the sequence of all the configurations that the Turing machine goes through. That's it. So we'll sort of assume that everything is a power of 2, the running time and the space usage for this presentation. And in that case, we can think of a computation transcript as just being a function that takes t plus s bit strings and has an output in some alphabet. And yeah, the computation transcript for a Turing machine can be described as valid if and only if every little window into the transcript is valid. So you can just look at a small number of cells, sort of locally checkable if you write down the right information in each cell. Yeah, this is not actually going to be a PCP by itself, of course, because there are many different windows that you have to check, like t times s, and it's possible, of course, for the computation to be incorrect, but most of the windows can look valid. So it should be no surprise that what BFLS does and what PCPs do is they take a computation transcript and they encode it with an error-correcting code. So now you'll have symbols in this encoded transcript that depend on the entire computation transcript. Turns out that you can use a linear code in BFLS. So yeah, this is the first ingredient in BFLS, and there are also some other polynomials that I'll get to a bit later. Okay, so we can start by just asking how you can try to efficiently evaluate the encoded transcript. And I'm going to do something a little silly and just ignore the coefficients for now. So we all know how to compute summations naively, right? You just go over everything and sum it up, but this would be too much work for us. It would be t times s, where we want something more like t. So we'll just start summing with the first configuration. Just like take all the cells in the configuration and add them into your bucket that just sums everything up. But this is like a little bit tedious, and you don't want to keep doing this. So when we get to the next configuration, instead we'll just look at what we got for the last configuration, and we can look at where this configuration actually differs from the previous configuration. So for example, maybe we'll see that in the previous configuration was 3, but now it just changed to 0. And so we just subtract 3, and then voila, we have whatever. So the sum for the next configuration. So you can keep doing this, and at the end, you'll get the sum of all the things in the computation transcript, and you'll have run in basically O of t time instead of t times s. So what we used is the fact that you can implicitly just enumerate all the changes that happen step by time step without explicitly just constructing each configuration. And now, what about these coefficients that I was hiding? These might seem to be a problem, and in general they would be, but they have a special structure to them in the specific linear codes. So everything is still okay. The specific structure is that it's a tensor code, but let's not get into that. Okay, so abstractly, we just use this simple observation that if you look at the summation of everything in a single configuration, that quantity is sort of updatable as you go from one configuration to the next. Okay, so I hope that was a pretty simple warm-up. Okay, but what about these other polynomials? I didn't even tell you what these polynomials are, but here's an example of some polynomial that's not exactly what you have in BFLS, but it's sort of a prototypical example in that it captures what we want to deal with. So specifically, it has this structure that it's like a linear function of some nonlinear stuff applied to another linear function, like sort of blockwise linear function, kind of. So just to sort of more graphically show what this kind of polynomial looks like and how you might go about computing it. So the inner summations the inner sums are indexed by like a y and an a, and these correspond to kind of taking your transcript and chopping it up into blocks. And then just the rest of the stuff, you sum everything within each block, square each thing, and then sum all of those. Okay, so this is just to make sure that we're all on the same page about what this kind of polynomial looks like. And the algorithm that's actually depicted on this slide for computing this polynomial would not satisfy our efficiency properties because you're actually enumerating many, many things. The space usage would be too high. So what we do instead is you start with the observation that, again, these inner summations are efficiently updatable as y increases. So one way to try to compute this polynomial more efficiently would be to assign some amount of space to each inner summation and just keep track of how that quantity updates as you go from time step to time step. The only problem with this is that the number of different inner summations could be too large. You might not even have the space to store a single field element for each one of those. So what if we just forget about most of the buckets and just keep track of one at a time? Because there's not going to be that much happening at any given time step. Only part of the configuration is going to be changing, and it will correspond to, at least in the Turing machine case, to like where the Turing machine head is, and that can't move, can't jump around too wildly. So as this Turing machine head moves around, you'll get a whole bunch of changes to just one of these inner sums, and every time you get a change, you can incorporate that into like your outer sum, basically. And so what happens when you like hit a boundary? All of a sudden, your Turing machine is making changes to another part of the configuration. And in order to know how that affects the overall polynomial, you need to know what the summation is for that part of the configuration. So you can just compute that, and anyways, the Turing machine will go ahead and move around, and every so often you'll need to like re-instantiate a new bucket. And yeah, so you can do this, and you'll use not very much space. The question is how much time you will take. So basically what happens is every time you have to like bring a new bucket into existence, you need to sum over everything in that corresponding region of the configuration, which takes time, roughly like 2 to the whatever is on the slide. But the point is that that cost is approximately the same amount of time that it takes you to get to a new block. So it kind of amortizes to not much overhead to actually reinstantiate these buckets. So abstractly what's going on here is that we've observed that the memory access pattern of Turing machines is pretty cache friendly. Like it sort of reuses the same like, blocks of its tape. And this is actually sort of related to what we do when we generalize to RAM programs. We like look at the cache behavior of these RAM programs. And anyways, I won't get into that much into that, but I'll just talk about some of the additional challenges that more of the things that I didn't have time to talk about in this talk. So the first thing I just want to remind you is that we were like all of this like super simple efficiency analysis relied on having a simple PCP that we could look at. And in order to actually do that, we had to sort of simplify the no signaling soundness constructions. I claimed that we could also generalize the construction from Turing machines to RAM machines. Just to say a couple of words about that, we looked at a variant of Turing machines that we call like tree machines that have been studied very sparsely in the past. So these retain some of the nice properties of Turing machines, that they have these like local windows that determine the correctness of a computation transcript while still having the ability to emulate a RAM machine. So I didn't talk about how the prover was going to be running underneath this somewhat homomorphic encryption scheme. I didn't talk too much about that, but it actually is not as bad as it sounds. The homomorphic computation that we actually need to run is a very low multiplicative degree, like log in the running time. And most of the computation is actually done outside of the homomorphic encryption. So in general, if you have a space S computation and you just stick it into a homomorphic encryption scheme, you'll get like a multiplicative increase in the space. But because most of our computation is happening outside of that, we still keep an additive overhead. Anyways, yeah, just to quickly summarize, this was like the previous work based on like sort of falsifiable cryptographic assumptions, and this is this work. So, yeah. If there's any questions, I'm very happy to take them, and also if you're interested, you can find more details in the posted version of the paper. If you allow more rounds, then you can. With Killian, not with. So you can achieve a better running time, but if you're talking about using Killian's approach, then there still is an issue with the space complexity, I think.
Right, exactly. So my question is whether this problem, if you want high efficiency, the things become easier if you allow more rounds. I mean, you have like an easier solution that doesn't need like no signaling PCBs and stuff like that if you allow actually more rounds.
Well, yeah, I mean, then you can just use that BFLS as a classically sound PCP and just do the same kind of efficiency analysis. So like we basically, like, there's like two parts. One is showing that BFLS is no signaling sound, and the second part is showing that BFLS can be computed with this great efficiency. So if you're talking about 4 rounds, then you can just forget about no signaling soundness and just use the second part. Oh, right, yeah, that's a good point. So you can, so there are the complexity, so there are ways to transform MIPs also into a 4-round protocol using like these sort of function commitments that use some complicated wholly homomorphic encryption stuff. But you can do that.